Hi, I'm John Thangaraja. I'm a professor of artificial intelligence here at RMIT University. I'm also the research director for the Center for Industrial AI Research and Innovation. And I also happen to be a lead CI on one of the next gen graduate programs on round two on AI techniques for emergency management and critical infrastructure. So in the next 15 minutes or so, I'll give you some examples of how we've used various AI techniques in practice, and hopefully I'll give you some insight into some different forms of AI that perhaps you have not seen as much before. So I'll talk about computer vision. This you would have known and heard about at least. So we'll talk about a few examples there, but then we'll get on to some generative AI examples that we've done well before ChatGPT and the like, so not using LLMs. And then I'll talk about multi-agent systems, which is really my core expertise of almost 20 years or so. And then I'll finish off on some fun examples where we get robots to play soccer. So let's start with computer vision. So computer vision is a machine learning technique where basically we train a computer to try and identify particular images or patterns within a particular image, right? So what are the applications of this? One of them is the work that we did with St. Vincent's Hospital. So in regards to prostate cancer. So 1 in 6 men in Australia over 60 gets prostate cancer, and nothing can happen, no symptoms will develop, and it'll all be fine. But for some, it can also be quite fatal. Unlike other forms of cancer, prostate cancer doesn't have a national screening program. However, men over 60 do fall down, hurt their hip and have other sort of injuries. So they end up in hospital and they get a CT scan, right? So the question was, can we use these incidental CT scans, the CT scans that were taken for a different purpose, to detect the presence of cancer? Now, MRI is the standard, it's a gold standard, and MRIs, a radiographer can look at it and they can detect that there is prostate cancer or not. But if you take a CT scan, it is less visible, right, to the naked eye, to the human eye. So we trained a machine, using computer vision, we trained an algorithm, a model, if you like, to be able to detect the presence of prostate cancer if there is in CT scans, and we had good success. And this is work that we did with doctors in St. Vincent's, as you can see from the photo up there. It was done during COVID, and so when we visited the hospital and so on, that's why we had all our masks on and so on. So that's one really great example of where we use computer vision in practice, because it saves lives. So here's another example where members of our team have used computer vision in this particular case in a factory setting, on a floor setting, with forklifts to identify potential hazards, and then ideally be able to prevent these things, because hazards when driving a forklift is actually quite common in these settings. So this was a linkage grant. Here's another example from hospitals to forklifts to livestock. So here we use computer vision to identify any potential issues with animals, right? So here is a cow walking through with a normal gait, and here this particular cow has severe lameness, right? And the way we can identify that is by using computer vision again to identify the gait, right? You can see the sort of skeletal structure there that's been mapped, the gait of the movement, and you can use that and by tracking that, you can identify if there's an issue or not. So there's 3 very different kinds of applications of computer vision. So let's talk about generative AI, the topic that everyone talks about today, and everyone's talking about ChatGPT or Bart, for example, right? This is very commonplace today. Everyone's heard of it, everyone's playing with it. But generative AI is not just about large language models and ChatGPT, right? It's well beyond that. You can generate other things as well. Okay, so we've been doing some work, for almost a decade or so on generative AI. So here's one example where we work with an industry partner who was creating this autonomous vehicle, and of course, there's learning that needs to occur in it for it to drive through different terrains. Now, the problem with this is that gathering data to train over this terrain is almost impossible, because you can't just get it to do 1,000 runs and in different settings in rain, in hail, sun, and so on, right? So the way we do that is we first capture the terrain, and then we synthetically generate new terrains that we can train our models over for this particular vehicle, right? So here's, for example, you take an image and then you abstract things out, and then you're able to generate new terrain. So as with most of the other work, you'll see that I've put in a link at the bottom. You'll get these slides anyway. So I'll put a link at the bottom here that you can go and look up if you'd like to know more information about the work that I'm presenting here, because of course I'm just giving you a very brief overview. But if you go and read some of the research papers or the web pages that are linked to in this presentation, then you can get a bit more information on them. So then let's move to multi-agent systems. So this is really the heart of my own expertise. Now, of course, leading an AI group for several years now meant that I've broadened my expertise and indeed the application areas that I'm in. But multi-agent systems is at the heart of where I started in AI. It was where my PhD was in. I'm working for over 20 years in this space. So let's talk about cognitive agents. Well, what are they? So cognitive agents are agents that can deliberate, right? They'll be like humans that we do. And there are common features of these cognitive agents, just like us humans. I'll go through it. Imagine there was a robot and it can see a ball, so it observes, right? I can see a ball over there. And then it deliberates, well, what should I do? Well, let me go walk up to it. Well, it goes up to it, and that's the action, right? So I see the ball, I decide that I'm going to walk up to it, and then I act on it. And then what do I do again? I observe again. Okay, I'm up the ball now. What can I do? Oh, maybe I should pick it up. So I deliberate, and then I act by picking it up, right? But then I do this autonomously. So without any human intervention, I can make these decisions by myself. So I'm autonomous and proactive. I see a ball there, and I make a proactive decision to go up to the ball and figure out what to do. I'm reactive. When I'm going up to the ball, if I see an obstacle, I'm going to avoid it, right? So I'm reactive in that sense. I'm rational. I see the ball. I'm just not going to just pick it up and throw it away, sort of thing, right? Or if I'm playing soccer, I'm not going to kick it to the opponent goals. I'm rational in what I do, and I try and learn. So over time, I'm going to learn how to kick the ball and perhaps learn how to play soccer. And indeed, we do with these robots, we do learn how to play soccer, and I'll show you some examples right at the end of this presentation. Okay. So some other examples where we've used multi-agent systems with industry partners over the years. Here's a few of them, right? So with the Defense Science Technology Group, which is much like a research organization, much like CSIRO, with very much a different focus supporting our Australian defense. We look at various simulations of complex behaviors, right? Mainly with human behaviors. Weather alert system that we did with the Bureau of Meteorology many years ago, again with in collaboration with researchers at CSIRO, we've been doing bushfire and flood evacuation models using agent-based simulation. We worked with a company called Real Thing on building conversational agents as a linkage grant some time back. We work with a company called AOS, Agent-Oriented Software, and they have various projects that use multi-agent systems. And again, more recently, we've been looking at human-machine teaming with these multi-agent systems, and humans coming in and working as true collaborators. And how do we do that? Again, this is work that we've been doing with the Defense Science Technology Group. We also have a project, a European project that we are part of. It's called C2 Impress. Again, there's a link here at the bottom of the project webpage. So this is a multinational project across Europe. And RMIT, as part of RMIT Europe, are also participating here, and we help out with the agent-based modeling aspect of it. But again, here, I'm putting a link here so that you can go and have a look at it. It's a very interesting project. Again, we use multi-agent systems and AI in these projects. So the one thing with multi-agent systems and AI in general is that we mustn't forget that the AI is part of a large system. Now, I know you can say, look, a data analysis problem doesn't require a whole system, right? You can just feed some data into it and you get an output, and you can run that in a silo. But if you think of a drone delivery system, for example, or a drone that does search and rescue, right? It can't just be one algorithm that does the learning and off you go. right? It needs to be a complete software system. And as such, you need a proper software engineering approach to it. So that's in the multi-agent systems field, we call it agent-oriented software engineering. So agent-oriented software engineering, meaning this software engineering techniques that is built on the well-established mainstream software engineering, if you like, but adapted and adopted to multi-agent systems. So the phases are the same: the requirement analysis, design, development, testing, and maintenance. And so we've done work in all of these areas. I'm just giving you some links here just to get you started if you're very interested. But in terms of the requirements, we use an approach called user and system stories. Again, it's from agile, mainstream software engineering. Basically, as a drone operator, I want drones to explore autonomously a given area so that they can find victims and notify me. So that's a particular use case, a user and system story, a user story here for a drone operator, right? And similarly, as a system story, the drone can say, as a drone, I want to explore an area assigned to me so that I can find victims. Here's my acceptance criteria. If it's a high priority area, then when the area X is assigned to me, I employ a particular plan called a cloud sweep. Okay, so these are just examples. This is how we capture requirements, right? So once you get the requirements, well, how do you translate that into the code? How do you translate that into a software system that implements these multi-agent systems? Well, you need a design methodology. And so at RMIT, we built a design methodology in-house. The latest version of it is called TDF, the Tactics Development Framework, and we've co-authored a book as well together with DST Group, because they've sponsored primarily a lot of the work that we've done in the past. And it's a successor to the Prometheus methodology, which again was built in-house here on how you design multi-agent systems. Again, if you're interested, please go look these up. And of course, designing the system, you've got to implement it, right? And so for that, you need what we call an agent-oriented programming language that would integrate with the standard software. So a lot of these are Java-based, but you get others as well. But most of the agent-oriented programming languages today are Java-based. SAL is one of them, Jack is another. These are what we use here at RMIT quite a lot. And I'll talk a bit more about SAL in the slides to come. But so here's TDF, just a very quick overview of TDF, the tactics design framework that I mentioned. I'm not going to get into technical details, but one thing I want to highlight here is that when we design these cognitive agents, we design them not in terms of objects, right? We design them in cognitive terms like goals, plans, beliefs, percepts, actions. These are the terms that we use as humans when we try to strategize, develop strategies and plans to achieve some particular goals, right? I mean, this is how we speak, and this is what we can relate to. This is very important, right? Because when you design such a system, you want to get non-experts to critique this. You want to get bushfire experts to look at this and be able to say, oh yeah, that makes sense. That strategy makes sense. And there's no point showing them object models. Hence why the need for specific AOSE techniques are needed. Hence why we've been developing these for many years now. Similarly, SAL is an agent programming language specifically catered for multi-agent systems. It sits on top of Java, right? And it also uses all the standard software engineering tools. So think of it as another level of abstraction, right? Another level of abstraction that allows you to implement multi-agent systems. Again, you've got to test and validate these things. There's a lot of research that we do in this space. Again, I'm citing some recent work and some past work as well, just so you get a feel for that. We've been doing this for a long time, and this is not a solved problem. There's a lot of research in this space that needs to get done when we actually apply these in practice. So let me quickly end up with some fun examples where we use robot soccer. So we use a lot of machine learning here, of course, in learning how to play soccer. And RoboCup is an international competition. It's been going on for a while. And the idea is that one day that you will have robot soccer players that can compete with human soccer players. So they're quite far away at the moment, but I'm sure bit by bit we are certainly making progress, and we'll get there one day. So RMIT took part last year in Bordeaux, France, and I'm really pleased to say that we came in fifth actually in the world, which is amazing. We took part after almost 15, actually almost 20 years actually. I got into AI, actually being part of RoboCup, way back in 1999, believe it or not. And the robots back then looked very, very different to what we do today. These are humanoid robots, now robots that we do. This is not actually our team because this is from a previous competition in 2018, but it's like a highlights package, so it makes it a bit better. But certainly, this is a really nice way to get students like yourselves and others involved, because it's, of course, robots are fun, right? But what we learn on the robot field or on the soccer field, getting these robots to play soccer, we then take and translate into other areas. We do make innovations here that can be applied to other areas, right? And as you can see, it's a whole lot of fun for everybody, and in getting to that stage. So on that note, I think I will end there. Oh, just last thing I want to mention also is the other fun aspect of these robots. So at the end of last year, at Christmas time last year, we took these robots out to the Royal Children's Hospital, to the cancer ward. And it's fantastic, right, to see, to put a smile on these kids and get them interactive, and also the enthusiasm that they showed for this. So, as we do interesting stuff with AI and cool stuff, I think we can also use it for social good as well. And I encourage you to think about these various different aspects as well. On that, I shall end. Thank you.